Okay, so I think it's about time to start. I want to thank Anli for his help and support in organizing this joint session of the HIO Colloquium Series and the IMAGE seminars. So it's my pleasure to introduce today's speaker, Dr. Ben Maruca. Ben is Charles Hartown postdoctoral fellow at the University of California, Berkeley, where he works at the Space Science Laboratory in the team of Stuart Bale. He got his two bachelor degree at the Carnegie Mellon University in Pittsburgh, one in mathematics, the other in physics. And then he pursued his scientific education in a very prestigious school at Harvard University. And he is an expert of heliospheric plasmas. And one of his expertise is certainly the statistical modeling of probability density functions of solar wind particles, mainly protons and alpha particles, but also electrons, I believe. So in Berkeley, he is involved in a number of atmospheric and space missions, among which there is this NASA balloon mission GRIPS, where he is the developer of the software, the flight computer of the balloon mission. So the spectrum of his research interests is really broad. I think this is enough, so I can give Ben the word.
Right. Thank you, Raffaele, so much for that generous introduction. And thank you for attending. I realize that this is a subject that's a little bit out of the normal range of research for NCAR, but there's certainly some overlap, and I hope you find it interesting. But in recognition of that, I thought I'd begin with a few slides just introducing the solar wind. So I apologize if any of you find this at all trivial. But I want to start with just looking at the sun. And when you look at images of the sun in visible light, this is one from SDO AIA in visible light, specifically 4,500 angstroms. The sun looks rather boring. You see a little bit of structure. You see some sunspots over there, and a little bit of granulation structure, but the sun appears largely uniform, devoid of structure. But then when you look at ultraviolet wavelengths, the picture changes completely. Again, this is from SDO AIA, and we're looking at the superimposed image of three different wavelengths, 211 angstroms, 193, and 171 angstroms. And these wavelengths were chosen very specifically because they correspond to prominent spectral lines in highly ionized species of iron and silicon and other elements. So the fact that you're seeing any emission at all at these wavelengths is indicative of very high temperatures, well over 1 million degrees Kelvin, well over 1 million Kelvin. And also, you'll see that unlike in the white light image, there's stuff emanating out from the sun, indications of an atmosphere that's known as the corona. This corona is highly structured. You see some loop structures, especially in association with these bright spots, these active regions. And in fact, many of these structures appear as little streams that seem to be moving somewhat radially out from the sun. So if you go further out, this is an eclipse image of the sun, you can see that the streams really are moving out. You have this outflow of plasma from the corona into deep space, and that's what we call the solar wind. In the corona, the plasma is heated, and it's also accelerated to supersonic speeds. And it comes out in these distinct streams. So it is highly structured. The solar wind is highly structured, and it's also highly variable. All of the parameters, density, speed, temperature, composition, whatever, they're all very variable from one stream to another, and even within a given stream. As the solar wind moves out, it carries with it the solar magnetic field out into deep space, and it goes out to about 100 AU, so well past Pluto until it hits the interstellar medium. One of the unique things about the solar wind is that among astrophysical plasmas is that it's available for direct measurement. Unlike any other astrophysical plasma, you can actually go into it and sample it and measure the particles and fields directly. You find conditions somewhat similar to the solar wind throughout the universe, but you can't go into an accretion disk or a nebula. But with the solar wind, we can actually go there and measure these particles and fields directly. And in the case of particles, this really lets you get access at the velocity distribution function. The VDF is just the probability distribution of particle velocities for a given species. And you can infer this from these in situ measurements of the particles. And from these distributions of particle velocities, you can derive the bulk parameters. So I just have a little cartoon sketch here of probability density of a VDF, a one-dimensional velocity distribution function. So we have probability density versus particle velocity. The zeroth moment, just the integral of this, would correspond to the density of whatever species this is. The bulk velocity is the mean, the first moment, and then the thermal speed, it corresponds to the second moment, so it gives some indication of the width. And thermal speed is just connected to temperature, so the Boltzmann's constant times temperature is equal to the particle mass times thermal speed squared. Now, I mean, this looks like a nice Maxwellian distribution. But of course, in reality, things in the solar wind are very complicated. You don't always get Maxwellian distributions. In fact, you rarely get them. And what's happening is you have a lot of processes going on. Even as the solar wind expands into deep space, you have heating and you have cooling and turbulence and waves. All of this is going on at the same time. And while all this is happening, you have very few collisions among the particles. It's a very low density medium, so particle collisions happen quite rarely, and so particles unable to exchange energy among each other preserve these non-equilibrium features. So what sort of non-equilibrium features am I talking about? Different particle species can have different bulk velocities and different temperatures. And specifically, my talk, when I want to talk specifically about differences in temperatures between protons and alpha particles, they're actually rarely found to have the same temperature in the solar wind. You also can get different temperatures along the axes perpendicular and parallel to the magnetic field. The presence of the magnetic field in the plasma creates direction-dependent transport coefficients. So heating and cooling can be more efficient along an axis perpendicular or parallel to the magnetic field. So as I said, I've been working mostly with protons and alpha particles and looking specifically at their different temperatures. Protons are really the majority ion species in the solar wind. The second most populous particle is alpha particles. Second most populous ion species is alpha particles. Protons, of course, are just ionized hydrogen, and alpha particles are fully ionized helium. The fraction of ions in the solar wind that are alpha particles varies quite widely, anywhere from 1% to 20%, maybe even a little bit more. And pretty much protons and alpha particles account for 99% of the ions you come across. So they really are the majority. They dominate the thermodynamics of ions in the solar wind. The observations that I worked with came from the WIND spacecraft's Faraday cups. WIND is a great instrument to work with, and the Faraday cups really provide wonderful ion measurements, specifically of the protons and the alpha particles. And WIND it moved around a bit, but it's pretty much fixed at a distance of 1 AU from the sun. It's in the near-Earth environment. It did sometimes go into Earth's magnetosphere, but most of the time it was in the solar wind and relatively close to Earth. So this plot here is the distribution of what I'm calling theta values. Theta is just the alpha proton relative temperature, T alpha over T proton, for all of the measurements that I had available at the time of this study, which worked out to be over, well over 2 million individual measurements of temperatures. And this is spanning over, well over 15 years. And one of the first things you might note, is that T alpha is almost always higher than T proton. The alpha particles are almost always hotter than the protons. In fact, you see alpha particles colder than protons only about 1.1% of the time. The other thing that's very striking about this plot is it's bimodal. You have two peaks. You have one peak here roughly around a theta value of 1, which is important because that's thermal equilibrium, equal temperatures. And then you have a peak here at roughly 4-ish, which would correspond to equal thermal speeds, since the mass ratio of alpha particles to protons is 4. And these are the two really critical values. So this is very suggestive of something going on. When you have equal thermal speeds, that's a very clear signature of wave heating, which is thought to be a very important mechanism for heating the solar wind. So there's a lot going on in the solar wind: heating, cooling, collisions, and these all affect the value of the alpha proton relative temperature differently. So my goal in this project was to explore how these observations of alpha proton relative temperature can be used to probe the collective action of these processes on the solar wind, and see if we can get some sense for what's happening to the solar wind as it goes from the corona to us in the near-Earth environment. So in this talk, I want to first explore the theta distribution in more detail, and then look at some trends in theta with proton bulk parameters, things like density, speed, and temperature, see how theta varies with those. Collisions I want to talk about in a little bit of detail, talking about collision times in the solar wind and calculating this quantity that's come to be known as the collisional age. And then finally look at collisional thermalization in more detail. So let's go back to this distribution. The first thing that I tried to do was just fit Gaussians to each peak to get some sense for where they are and how wide they are in a quasi-quantifiable way. And when you do this, you find that the peaks aren't really aligned with those nice special theta values of 1 and 2. You have the one narrow peak here, it's significantly above 1, and this higher peak is significantly above 4. It's actually at 4.5. But even setting that aside, these two peaks don't really account for most of the data. About half of the data or more are either in between the peaks or in this high tail. Now, I don't think that there's any particular reason why you would expect these peaks to have a Gaussian structure, but it is certainly suggestive that there's something a little more going on than just two populations that are overlapping. And especially these very high values above 4, so super mass proportional temperatures, are very suggestive of strongly preferential heating of alpha particles. Another thing that I took a look at was the temperature components. As I said, you can have different temperatures perpendicular and parallel to the magnetic field. So instead of just looking at what's called the scalar temperature, I also looked at the ratio of the perpendicular temperatures and parallel temperatures, and they're shown here in this plot. And overall, they look pretty similar, all three. When you're looking at the components, the peaks are a little bit shorter and broader. Probably the most notable deviation is in theta parallel, the parallel temperature ratio. The second peak is very mushy. It's more of a ledge. ledge or a plateau as opposed to a distinct peak. And the theta parallel temperature ratio is significantly higher than the theta parallel temperature ratio. The second peak is very mushy. It's more of a ledge or a plateau as opposed to a distinct peak. And the theta parallel temperature ratio is significantly higher than the theta parallel temperature ratio. this could be suggested, could suggest that the heating of alpha particle, the preferential heating of alpha particles in the parallel direction is relatively inefficient, but I wouldn't, I don't think that that can be drawn, that conclusion can be drawn exclusively from this plot. It's worth noting that both components, perpendicular and parallel, theta values exceed the scalar value at extreme theta, so beyond 7 or so. And that means that you see extreme preferential heating of alpha particles in both the parallel and perpendicular directions. So there has to be some preferential heating in the parallel direction as well as in the perpendicular. But the fact that they exceed the scalar suggests that they're not happening at the same time, that you have separate parallel heating and perpendicular heating mechanisms that produce extremely large alpha particle temperatures relative to the proton temperature. So the preferential heating of alpha particles is something that's well observed, and it's also observed in other heavy ions relative to the protons. Of course, theta equals 1 is the result is thermal equilibrium, and this can result, and this is the natural tendency for the plasma as collisional relaxation takes over. As you just allow particles to scatter, they eventually exchange energy and momentum until temperatures come into equilibrium with each other. As I said, a theta equals 4 value means equal thermal speeds, which is very indicative of wave heating. You see this sort of mass proportional heating in other ions as well as in alpha particles, and this has been seen with many spacecraft, including IC-1, Helios, Ulysses, and SOHO. This plot is taken from Hefty et al., and using SOHO data, they looked at they compared the temperatures of various ion species, looking iron, oxygen versus hydrogen, and iron versus hydrogen. And in each case, the solid line corresponds to equal thermal speeds, so mass proportional temperatures, and the dashed line corresponds to equal temperatures. And really, in all cases, you see that the observations are dominated by equal thermal speeds, this sort of mass proportional heating. So what happens at theta values greater than 4, the super mass proportional heating, where you really get the preferential alpha particle heating? It's unclear how this happens exactly, but there are a lot of theories, of course. There's been a lot of discussion of drift instabilities. It's very frequently observed that alpha particles have a velocity, have a speed that's greater than the protons, and that this drift can be so significant that it can cause instabilities to develop. And some theories have suggested that when that happens, that energy is preferentially redirected into the alpha particles. Alphane wave turbulence has also been shown to possibly preferentially heat alpha particles, especially in the perpendicular direction, as has resonance with ion cyclotron waves. There was a recent paper by Casper et al., PRL, that I was co-author on, looking at wind Faraday cup observations, the same data set that we're looking at here, and finding some pretty compelling evidence that ion cyclotron waves were responsible for a lot of this heating, preferential heating of alpha particles. And we were very excited about this. And then a couple months later, Ben Chandran's group pointed out to us that actually you could get the same signature from Alphane wave turbulence too. So it's very much an open question as to what's responsible for this preferential heating of alpha particles, but it's very clearly present in the data. So setting aside just the plane distribution of theta values, I want to look a little bit now at how theta trends with various proton bulk parameters. And specifically, for a start, at the proton radial speed, just the radial speed at which protons are moving out, the solar wind speed, as it's often called. And this is a very typical thing to do in heliophysics, to categorize solar wind based on its speed. Lots of discussions about slow and fast wind. Indeed, this is well justified. Slow and fast winds seem to come from different sources in the corona. And there's a very strong correlation of proton density and proton temperature with speed. In the slow wind, you see a very high density and low temperature. The fast wind, in contrast, is relatively diffuse and hot. This suggests that there are different heating and acceleration mechanisms for slow and fast solar winds, so it's quite possible that you would get different theta values in the slow and fast solar wind. So what we're looking at here is a 2D distribution of alpha proton relative temperature versus solar wind speed. And what I've done here is the color scale is linear here, and each column has been normalized. So the red region indicates the most likely theta value for a given solar wind speed. And as a little bonus here, this is just the distribution of solar wind speeds on their own. And you'll notice that there is a pretty clear trend, an overall increase in theta with solar wind speed. There's a little bit of a drop-off here, but at very high speeds. But that seems to be a systematic effect that, once you get at these very high speeds, alpha particles, they start to fall out of the energy range of the instrument. So this doesn't seem to be physical. It's more an instrumental effect. To quantify this trend, I use the Spearman rank correlation coefficient, which I emphasize is different from the more typical Pearson correlation coefficient, which measures linearity. The Spearman rank correlation coefficient measures monotonicity, so it doesn't rely on the underlying trend being linear. And it's also less sensitive to outliers. And when you calculate that correlation coefficient, you get 0.607, which is pretty significant. There's certainly a lot of scatter, but there's a pretty clear trend. So in slow wind, you tend to see theta values about 1. You see thermal equilibrium. As you go, you see the larger theta values mostly in the fast wind. So what we can do then is break this distribution of theta values into two distributions based on one for the slow wind and one for the fast wind. So I had my cutoff for the slow wind be 375 kilometers per second, and my cutoff for the fast wind be 425 kilometers per second. And these are the two distributions that you get. So this is for the slow wind, and this is for the fast wind. And it does a reasonably good job of separating out the two peaks. The slow wind seems to be mostly responsible for the lower peak, and the fast wind seems to be mostly responsible for the upper peak. But even so, there's a lot of overlap between these two, and even in the slow wind, you have a really long tail. You're still seeing very large theta values in the slow wind, and in the fast wind, you see some low theta values. So it's not a real, it's not a complete separation. It doesn't fully account for the two peaks.
Does it depend on the definition you use for fast and slow wind? By the threshold you decide to discriminate between fast and slow?
Yeah, certainly you're certainly going to see the exact distributions change as you move those thresholds. You can get a little bit more separation by moving those thresholds farther away from each other, but it doesn't improve that much. Also, there's sort of a philosophical issue with doing that, because then you're cutting out more and more solar wind. As it is, we're taking a big chunk of the solar wind and saying that it's neither fast nor slow, it's sort of in between. And making that larger and larger, it kind of defeats the purpose of having a slow wind and a fast wind.
Could you try to do the same thing using discriminant, not the velocity, but helioactivity?
I have not, but wind, it's mostly confined to the ecliptic, right. So we don't get a good sampling of different heliographic latitudes. Yes. So you can sort theta values not just by proton radial speed, but by other bulk parameters. We also looked at density and temperature, and you get a trend in each case. With density, you get probably the weakest correlation. You get the weakest correlation coefficient. And like the case with solar wind speed, you kind of break into two distinct populations. It's probably more dramatic with density. There is this sort of scatter down here at low density, but that's just the instrument sensitivity coming into play. You need at least some particles to come into your instrument to actually get a detection. The strongest trend that we found among the three was with when we looked at theta versus temperature. And it's kind of interesting that it's not two distinct populations, but it's a smooth trend. Now, the skeptic in you might be wondering, well, of course theta is going to be correlated with proton temperature. Theta is the ratio of alpha to proton temperature. So of course it's going to be correlated to itself. But if you think about it, if the alpha particle temperature was uncorrelated with the proton temperature, then the trend would be going in the opposite direction. So there's something else going on here beyond correlation with itself, that there is some trend connected with the temperature beyond just statistics. And we believe that that something is particle collisions and collisional thermalization. So we have these deviations from entropically favorable conditions, different temperatures, different bulk speed, different bulk velocities, and they're caused by the various mechanisms such as heating and cooling and acceleration that are happening in the corona and then also in the solar wind as it expands outward. Particle collisions act to keep these processes in check and to reverse them and to bring about thermal equilibrium. Collisions among particles exchange energy and momentum and bring you to maximum entropy, which would be thermal equilibrium. And that's assuming in the absence of sustaining processes. The rate at which this collisional thermalization happens can be quantified by the collision time, tau, which is the time that it takes for collisions to significantly alter some aspect of the VDF or VDFs. It's kind of a squishy definition. So how significantly is significantly, you get some factors on the order of 2 and 3 involved. And some aspect, I worded it this way because there are different collision times for different non-equilibrium features. There's an isotropization time for bringing T-perp and T-parallel into equality. You have momentum and energy exchange times that are different, and they can often be vastly different. I'm not going to dwell on these equations too much, but one definition that's kind of useful is what Spitzer called the self-collision time for a given species J. There's the formulation for it. It depends on the temperature and the density of the particles, and that would be the Coulomb logarithm lambda. And in the solar wind, when you look at the self-collision time for protons, it can serve as a good generic time scale. It gives you a sense for how relevant collisional processes are in a very general sense. And what you can do is you can compare the collision time then to the expansion time, just the time it takes your plasma to go from the sun to you at a distance r. So for the proton self-collision time, then you get this value. And this is what we call the collisional age of the plasma. When collisional age is 1, you've had one collisional time elapse as the plasma comes to you. So values much less than 1, the plasma is not very collisional, it's collisionally young. When collisional age is much greater than 1, it's highly thermalized. So some caveats. This is a very simple way to look at things. You're assuming that parameters are constant radially, which is definitely not true. And you're only considering at any one time one definition for the collisional timescale, so it doesn't give a very good detailed look at the collisional thermalization of the plasma. Even so, it proves to be a very useful parameter, because if we plot theta versus collisional age, we get a very strong trend. In fact, this trend is even higher than the correlation of theta with collisional age is even higher than with temperature. This is really the strongest parameter. The best predictor for theta values that we have is collisional age. But as I said, it's a naive analysis, and we can do a little bit better. And this is really what I wanted to do, try to find a more rigorous analysis. The first thing to address is the fact that you have bulk parameters that change with distance. Observations with the Helios and Ulysses spacecraft allow you to see how the typical value of these parameters changes as a function of distance from the sun r, and very often they form these sort of power law trends. So the fact that you have these radial scalings in density, velocity, and temperature have an impact on how we deal with collisional age. For my analysis, I was using the observations reported by Hellinger et al. In 2011, and they found that density, proton density scales as r to the negative 1.8, and temperature, proton temperature scales as r to the negative 0.75 based on observations of fast wind with both Helios spacecraft. If you add in the requirement that proton flux is conserved, that gives you a proton velocity scaling of power law with an index of negative 0.2. So what I wanted to do was to use these trends, these radial trends in these parameters, to infer some radial profile for the alpha proton relative temperature. So, like any enterprising space physicist, I pulled out my NRL plasma formulary and looked up the equation for collisional thermalization of two particle species in a plasma. And when you do this and put in some basic assumptions about the thermodynamics of the of the plasma, you get out a differential equation that expresses how the alpha proton relative temperature varies as a function of distance from the sun. And the beauty of this is, and it's a little intimidating, but really it's not that bad. It's a relatively simple model. I will first state a couple caveats that went into the analysis. I assumed a steady state, and I neglected other sources of free energy. So I was only looking at differences in temperature. I was ignoring the relative drift of the two species, their different bulk velocities, and also temperature anisotropy I neglected. And I had no explicit treatment of heating or cooling or any of that. However, because this is a differential equation, I can put in typical heating and cooling rates, take them into account by putting in the radial trends for proton density, velocity, and temperature. Something else that's very interesting is that this differential equation looks an awful lot like the expression for collisional age. In particular, the key factor, density over solar wind speed, temperature to the 3/2, shows up very prominently in both. So this could be part of the reason why collisional age, despite all its flaws and assumptions, actually isn't a bad proxy. Another thing worth noting is, as you would expect, as you go to very large distances, things have to eventually thermalize, so this equation always trends to a theta value of 1, so equal alpha particle and proton temperatures. So what you can do then is take a set of values at one value of r for theta, proton density, proton temperature, proton velocity, and then infer a value of theta at some other r. And that's what I did. So I took all of the measurements that I had from the WIND spacecraft, all 2 million measurements, and one by one, I went and inferred a theta value at some other r. I plugged them into that equation, computed what it would be, and I said, well, okay, we made measurements at 1 AU. Let's go closer in right to the edge of the corona, a distance of 0.1 AU. And what is the alpha proton temperature ratio here? And this is really something that very much surprised me. So this is the old distribution right here, measured at 1 AU. And here's what I got for the inferred distribution of alpha proton relative temperatures at 0.1 AU at the edge of the corona. And remarkably, the bimodality completely disappeared. There's now just a single peak. And it looks an awful lot like this fast wind peak, both in terms of location and width. I am not saying by any stretch of the imagination that this is definitively what the distribution of alpha proton relative temperature looks like in the outer corona. Definitely not. I recognize that this is a relatively simple analysis, but what it does show is that you don't need to resort to different source models for the slow and fast solar wind to account for the bimodality. The bimodality would happen anyway just from collisional thermalization, that you get this sorting out of the plasma as some plasma isotropizes or thermalizes more quickly than other plasma. And this suggests potentially very similar heating mechanisms for the slow and fast solar wind. A few notes about this plot. There's a pileup down here at low theta, and this is from the 1.1% of measurements with the measured value of alpha proton relative temperature less than 1. I'm not sure what to make of these measurements. Maybe the model just fails for them. There's also the possibility that measurement error comes into it because we only have a finite accuracy for T alpha values and proton temperature values. Another thing to note is this very long tail in the distribution. Where does that come from? Do we really believe that the alpha particle temperature can be 10 times greater than the proton temperature? I'm not sure. Part of this could be that we're neglecting other sources of free energy, that when you go closer in, a lot of that free energy could be tied up in differential flow between the protons and the alpha particles. We do have some observations from the inner heliosphere. Helios observations point to typical values for the alpha to proton temperature ratio of 3 to 4.5. But then recently, MESSENGER, which is over at Mercury at around 0.4 AU, found very large values for theta. They found T alpha over T proton values of 9 on average, sometimes ranging into the teens. So I think the observations, there really aren't many, and it's very unclear what the alpha proton temperature ratio is in the inner heliosphere, but it could potentially be quite large, and maybe this peak isn't as unphysical as I initially thought. So just to wrap up, I've been in this project. I was exploring the distribution of alpha proton relative temperature values using wind Faraday cup data, and it has a very bimodal distribution. You have a narrow peak approximately corresponding to thermal equilibrium, and you have a wider peak at approximately equal thermal speeds. There are very clear trends in the alpha proton relative temperature with proton density, proton bulk speed, and temperature. And among those three parameters, you have the strongest trend with proton temperature. And in this case, it would seem that the fast wind isn't hot, but that the hot wind is fast, that the proton temperature is being more predictive of this than the proton bulk speed. But even beyond that, you get the strongest correlation, in fact, of alpha proton relative temperature with collisional age. And the key result of this project was the more sophisticated treatment of collisional thermalization using a very basic model for the process. We took observed values of the alpha proton relative temperature and extrapolated them back closer to the sun and found only a single distribution, a single peak, a single mode in the distribution of theta values, which really hints at the slow and fast wind being, at least in this regard, much similar than was previously expected. So I'll take any questions now.
You guys have questions? I have a question. On the last plot you showed,
yes.
You know, the possibility to distinguish between a fast and solar wind in ecliptic is related somehow with the solar activity, right?
Yes.
So you can't really see fast and slow streams only when you have a low solar activity. The situation is less clear when you have high solar activity, because the sun's pole gets to the equator, so you can't really distinguish fast and slow streams. So you say that you average how many years of data in
15. It was probably actually closer to 16, 17, with some excisions, because wind spent some time in the magnetosphere and we had to cut those data out, but
right.
Even so, it's a pretty big chunk of data.
So my question is, in these 15 years, of course, you have at least one entire solar cycle where when the activity switch from high to low. So there are periods when you can't really disentangle the fast and the solar wind. So I'm wondering whether this plot would look different if you could conditionate your analysis to the solar activity, like doing the same thing, but restricting the set of data you use to periods when you have low and high solar activity. Because you showed in the previous slides that there is a correlation between those two peaks and the wind velocity.
Right.
And it's a very good correlation. I mean, although you have these tails in both cases. So have you tried to do something like that? I mean, to do a conditional analysis where the condition is the solar, some threshold in solar activity.
Right. I have never tried pulling apart, doing sort of looking at like yearly plots of theta values. I'm not 100% sure what we would get. I mean, certainly at times we would see more solar, at different points in the solar cycle, you would see more or less of one type of wind versus the other. Although you seem to be defining slow and fast solar wind in terms of source region.
Right, in terms of velocity, but what really happens is that the difference in velocity is because the points where the location on the sun where the winds originate are different.
Right. So if we wanted to do that, so really the ideal way to do that then would be to look at charge state. Right. I mean, looking at the abundance of oxygen +6 versus oxygen +7, which gives some indication of the freeze-out temperature, the freezing temperature in the corona, and provides a reasonably good mechanism for sorting out the type of source region that it came from. Unfortunately, wind doesn't have charge state, any means for measuring charge state. The ACE spacecraft, which is located at the first Lagrangian point, which is where wind has been for some time, does have charge state data. The only catch is that it was launched much later, and so, but for at least some of the data, we could actually use those charge state data to try to separate out wind from different source regions. But that might be worth doing. I'd be curious to see what it would produce.
Yeah. Okay.
Oh.
Maybe it's a dumb question, I guess. I don't know that much about solar wind. In the solar wind plasma, does electron play any role in the thermalization process?
Yes and no. When you look at the collision rate between ions and electrons, it's very, very slow. I just saw a plot on this last month, and I think the largest value that they saw for the collisional age for that interaction, the ion-electron collision time, was like 10 to the -2, 10 to the -1.5. So you never see many collisional timescales evolve for ion-electron energy exchange. That having been said, you do still have these fields, the magnetic field, and you have waves that could mediate the exchange of energy of electrons to protons. Electrons certainly do seem to be carrying a lot of heat flux, which definitely plays a role in the evolution of the solar wind overall. So electrons could be playing a role. And it's unclear exactly what that role would be, I think, at this time. It's very much an open question, how much energy is exchanged between the two, ions and electrons.
And bipolar diffusion, they're not important at all.
I'm sorry?
And bipolar diffusion.
Bipolar diffusion.
And bipolar diffusion between the electrons and ions.
Yeah. Oh, yeah. Yeah. It shouldn't be too relevant. Yeah.
So I have a last question. Can you identify a threshold in the distance where the bimodal distribution will appear? I mean, the closer you are, the more those two peaks get closer, right? Mm-hmm. But at some point, you should be able to clearly distinguish the
right.
So
right. I've been meaning to do that, to actually produce this plot at bunch of different R's and sort of overlay them. Yeah. And show the first peak, show the second peak evolving, and then the first peak gradually vanishing. Yes. I have not done that yet. I tried a couple different R's, and I mean, so yeah, I don't know off the top of my head at what point it really clearly shows up. It depends a little bit on what radial scalings you choose for the proton parameters. And that certainly affects the location of that peak that you predict,
Right.
but not as much as you would think. It shifts around a little bit, like instead of 5.38, you might get 5.0 or 6.0, 6.5, and the width would change a little bit, but I was really surprised. You could put in some totally crazy numbers for those radial scalings and still get more or less the same result.
I see. Okay. No more questions? Okay. So thank you, Ben.
Thank you.